All right, we are recording. Any questions, anybody? Okay. All right, maybe I missed something in the chat. Hello, everyone. Okay. Okay. Sorry, I'm having some Zoom issues here for a second. All right. So what we're going to do today is talk about some review some items and maybe talk about some new things, but I think most of this is going to be review today. First, we're going to do a little bit of a lecture discussion with reviewing what are units, what are significant figures, what is precision, what is accuracy, what is uncertainty propagation, what is error analysis. And then we'll break into groups and do a few little some group work, answer some questions, and then come back and give our answers to the group and check correctness. And then we will look into different kinds of uncertainty. If I have a meter stick, or if I have a digital gauge or a stopwatch, do I determine uncertainty the same way for all those things? No. So we're going to talk about the different ways to determine things. Okay, and here are the groups based on the feedback from the survey. I've tried to put groups together where people got to work with people they wanted to. So let me know if you see an issue with any of these groups, or with your group, I mean. But I think everybody should be happy. And I came up with some very clever names for the groups. You're all a measurement device. So we have the photodiodes, the pressure gauges, the voltmeters, the Geiger counters, the calipers, and the thermometers. So I will try to put you into group, like breakout rooms, based on these breakdowns here when we split
Dr. Hester, I think I'm in two groups.
Are you?
I think I'm in photodiodes and pressure.
Well, you're going to need to be like doing some superposition there. Okay,
right,
I'll take you.
No problem.
I think, is that the same number? Yeah, I'm just going to arbitrarily take you out of the pressure gauge group. Henry, thank you for showing me that. I thought I counted a few times. If anybody's missing, let me know.
I see
Thought I had
one
just
Ethan,
the right
but
number.
there's two Ethans.
Okay, any questions?
I see I see one Ethan, but I don't see another Ethan in the list. So
because
there's two Ethans.
Well, I think I meant to put two Ethans instead of two Henrys. So we'll fix that. Did I already have R on the other one? Okay, does that fix it? Okay. All right, let's talk about some definitions of things. These things that I was saying earlier. I don't think we need to go too much over what are units. I'm pretty sure you all know what units are, and you have a very good understanding of units. And also with significant figures, we're not going to really review that much. I'm going to assume you know what's going on with at least doing math with significant figures. I know you've done that before. So we're not going to review that too much. These other things we are going to talk about a lot because a lot of these terms are used incorrectly by a lot of us, including professors. And I definitely want to clear up any confusion with that. I do it too. I'm sorry, we all do it. I'll try not to ever again, but it happens. So quickly, we will review what are the SI units. Here they are. There are 7 of them. Length, time, amount of substance, current, temperature, amount of light, and then mass. So we have a unit for all of those quantities. And all of the other units that you've come across for length or for temperature, you know, are other units you might see in classes, but these are the ones that we use as our you know, standard for class and for lab. In medical physics, we have all kinds of weird units just because that's the standard in that field. So you do come across other units, but in terms of teaching, we're going to stick to these in this class and in your lab that you're taking with this class. Okay. I don't think you'll have any questions, but do you have questions about units? Anybody? All right, a little bit different, significant figures. So significant figures are usually like something that were just told to you in the past, or maybe it's something, a measurement you did in lab, an introductory lab, and you probably didn't have to do a lot of math with those significant figures. But you're gonna do that now in this class. So we're not gonna get into that today because that's a big part of this class, is learning how to take those uncertainties and do math with them properly to find some kind of final uncertainty. It's not a simple exercise. So we're not gonna talk about that a whole lot today. That'll be throughout the semester. But today we do want to talk about significant figures and uncertainty and how those two things are related. Okay, so I'm going to refer to the document on the As You Learn page. Did I lose the As You Learn page? Sorry, I thought it was up here. Okay, so here's our As You Learn page. If you scroll to week 1, we have this Introduction to Measurements and Uncertainty document. So this is a document that you all were given in Introductory Lab 1150 and 1151. It is 29 pages long, 23, excuse me, 23 pages long. I'm not sure I trust that you all read this document in great detail, because it's probably the most boring document I've ever seen. One of the top 10. So we're going to hit the highlights for what really matters in this class. There's a whole lot of text here because if you need to go back and review something, then you can go read it in this document. We're not going to go through all that today. We're just going to hit the basics and the highlights. So the next kind of vocabulary term I want to talk about is uncertainty. This document open. So what is uncertainty? And how does it relate to significant figures? Okay. So according to this document, it's not really perfectly defined, but uncertainty is basically the degree to which a measured value is not certain. You never have a completely certain measured value. There's always some little bit of like, I don't know, involved. And we have this text here, kind of large, bold font. You decide the uncertainty. That doesn't mean you just get to make it up and like, you know, arbitrarily just say, oh, I'm going to just say that it's 1 gram, plus or minus 1 gram for my 50 gram measurement. That doesn't mean you just arbitrarily decide. It means you think about all the different factors that might contribute to the uncertainty in your measurement, and then you decide. You think about the rules, and then you think about, well, is there anything else going on that would make this uncertainty a little bigger than my rules are telling me for some reason. And then I would incorporate that into my uncertainty. So that's what I mean by decide the uncertainty. Okay, anybody want to say anything? Got a question? Let me keep. Okay. There's two important statements here that I want to definitely cover. The first one is the uncertainty should have the same decimal place and units as the measured value. If I am measuring 50 kilograms, I should not have an uncertainty of meters per second. And if I'm measuring 100.0 kilograms, then my uncertainty is going to be plus or minus point something in that 0.0 place. We'll do some more examples, so you'll see what I mean. But that's not always the case. Like in chemistry, sometimes they don't have the same units. So this is not like a shared worldwide rule. This is a physics rule for physicists and metrologists. People doing metrology are people who are, they are scientists of measurement. Okay, and so this is based on these rules that we have here. I'll show you in the references section are based on what has been put together at NIST by that metrology group, and they are, you know, officially scientists of just measurement. Oh, no worries, Sabrina. Thanks, Sabrina. Okay, let's look at the next statement about uncertainty. Number 2. These significant figures are determined by the uncertainty. First, I measure my thing, I determine my uncertainty, then I write down my value, and I know how many significant figures I have because it has to correspond to my uncertainty. So for example, if I look up here, 25.28 millimeters plus or minus negative 0.2 millimeters is not going to work. The precision doesn't match. I have 2 digits after the decimal here, and then I have 1 digit after the decimal here. It has to be 2 and 2 or 1 and 1. So it is okay to say 25.3 millimeters plus or minus 0.2 millimeters. If I say that the uncertainty is 0.2, then I have to make my precision match that in my value. Any questions? Okay. What is uncertainty propagation? That's our next item in the list from the agenda. Here's the agenda. Now we want to talk about, oh, sorry, precision. That was the next thing. Okay, so precision, we're going to go to that PDF. If I go to the first page, it gives me a bunch of links to kind of follow. And there's one down here for accuracy versus precision. All right, so before we flip to that, who can tell me what is the difference between accuracy and precision? Anybody? Yeah, just speak up. Go, Alex. See you right.
Accuracy means that the responses are close to the correct value. Precision means that the various values you get are all clumped close together. So you can have something that's inaccurate but precise, in which case all the values are away from what should be the correct value, but they're all clumped together. Or you can have something that's accurate but not precise, so everything's kind of near the correct value but not near each other.
Okay, yeah, so if I go to this page here, it gives us a nice, oh, sorry, I thought it would take us there quickly. There's a nice illustration of what Alex was just saying, right here. All right, so if we have something with lots of accuracy, it is correct. That means when we are, we have a lot of accuracy, our measurements are close to the proper value. So that's trying to be shown here with this kind of bullseye, where the measured values, the yellow measured values, are overlapping with the red, like known correct value. If we have all of those things outside and not really close to the known value, that's low accuracy. Basically, accuracy means, is it right or wrong? Here we have correct values. Here we have incorrect values. Whereas with precision, precision is more about how similar are my values. So in this case, my values are all not as similar as they were before, but still kind of centered around that central spot. So they're still accurate, they're still right, they just kind of suck. My precision is low. And then over here, they both suck. Low accuracy, low precision. It's not really centered over the correct value, and the things are kind of spread out. So which of these quantities is related to uncertainty, and why? Somebody tell me. Accuracy.
Well,
Precision.
things that
Yeah, go ahead.
things that have less precision will have a greater uncertainty. So less precision is greater uncertainty. So it's mostly,
Okay.
I would say uncertainty is more related to precision than it is accuracy.
Okay, and how are precision and uncertainty different?
Well,
Somebody else besides Ethan and Alex. Yeah, Caitlin, were you raising your hand?
Yeah, accuracy is hitting the same spot every time, and precision is, oh no, accuracy is hitting the right spot, and then precision is hitting the same spot.
Okay, but how are uncertainty and precision different?
You could be precise but still not be accurate, so the uncertainty is wrong. Or wait, what was the question?
Uncertainty. Okay, so like, 25.00 plus or minus 0.02 meters. I have 0.02 meters of uncertainty. Okay, what is my precision for that measurement?
Is it the 0.02?
Yeah, it's the same thing.
Okay.
Pretty much, yeah. My precision of my measurement is basically like determined by my uncertainty. If I have a really precise measurement, I have a really small uncertainty. If I have a really not precise measurement, I have a big uncertainty, basically. So they're not exactly the same thing. So Caitlin, I kind of put you on the spot there, and that was a good job that you did. And thank you, Ethan and Alex. But they are really similar concepts. Not exactly because of that like bullseye picture, but when we're talking about precision of a measurement and uncertainty of a measurement, they're basically the same thing. Okay, next is uncertainty propagation. Sometimes people call that error propagation, but that is really not what they should call it. It should be called uncertainty propagation. So what am I talking about with that phrase? What does that mean?
This is kind of just a guess, but would it be like the more you repeat something, the more error or uncertainty would accumulate in, like, say, a measurement or something?
Okay, that is related, but it's not exactly what uncertainty propagation is. But that's a related factor. Thank you, Brendan. Somebody else want to try? What is uncertainty propagation?
Is it how the uncertainty affects your measurement?
No, I don't know. Maybe. I'm not sure. That's not what I would call it. But
Like
It could be interpreted that way.
Maybe that's not the best way to say it. Is it how, like what?
Okay, let me just
I'm sorry, I'm
tell
trying
you
to
what it is.
gather-
Okay,
trying to gather
y'all,
what-
I don't think you've learned this yet. This is where you learn this class. So let's just define it here. I didn't expect anybody to really know. Okay, so let's use my example of measuring the speed of light. Let's say I measure the time it takes for a pulse of light to travel a mile or something. So I measure the mile with some kind of measurement device for length, and I measure the amount of time with some kind of detector, and I'm going to have an uncertainty in my time measurement. And I'm also going to have an uncertainty in my length measurement. And I got to do some math with those measurements to find the final value of the speed of light. I need to do some, like take a quotient, right? I could take the distance and I divide by the time. So I have a distance quantity plus or minus some uncertainty divided by a time quantity plus or minus some uncertainty. So I have to have some final uncertainty of my speed of light value. I'm going to have some final value, 3.99 times 10 to the blah, 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 plus or minus blah, blah, blah. I have to take those measured uncertainties of my length and time and do something with them, do some math with them to find a final uncertainty. And that is what uncertainty propagation is. That's a really simple example. It gets way more complicated than that. And that's what we learn in this class. If we have to do, a 10-step math problem to get from my measured quantities to my final quantity, I'm going to have a lot of different steps with my uncertainties as well on the side in parallel. So the math that I do with my original measurement uncertainties to get to my final uncertainty of my calculated value based on my measurements, that's what uncertainty propagation is. And people call that error propagation all the time. And it's really not error propagation. It's uncertainty propagation. Even in this document, it says error propagation. So I'm going to try to say uncertainty propagation all the time.
So
Anybody have a
are
question
error and
about that?
uncertainty
Sorry, go ahead.
different things? Are error and uncertainty two different things?
Yes. Yes, they are.
They are.
Yes.
Okay.
That is a fabulous segue to my next item that we're going to talk about. Unless anybody has a question or comment about uncertainty propagation.
So the uncertainty propagation is just like the final values. So that would be like in meters, like per second. It's like combining of like the time measurement
Yeah,
and
it's
like
the
meters.
process of getting to
Okay.
that final value. Yeah,
Okay.
exactly. Yes, that would have meters per second units. That final uncertainty. Anybody else? Question, comment? Okay. So we're then going to move on to error. What is error? I think that was the next thing. Yes, error. It's the next thing on my agenda. What is error?
The amount you are from the accepted value of something.
That's right. So it's basically like, how wrong are you? If you have big error, you're really wrong. Your value is way off of what it's supposed to be, your measured value. If you have small error, you did a great job and you did a lot of things right. There's a lot of ways to do it wrong. So if you have really small error, awesome, that's great. And you don't have to explain a lot because you like did everything right if you have small error. If you have big error, you got a lot to explain. Like maybe it was this, maybe it was that. I may have you've been using my calipers wrong. Who knows? Lots of ways I can get a big error. Lots of ways I can mess up my measurement or my calculations or get my model wrong. Lots of ways. So error is how incorrect you are. Sometimes you don't know what the accepted value is. We all have a way to look up the current speed of light. and know, to pretty high precision what that is. But if you're measuring, if you have like a string and you're measuring some material property, the elasticity or something of the string, it might not be a known value, So sometimes you're just going to compare some measured things to some other measured things. And how different they are from each other might also be called error. But pretty much in this class and in senior seminar after this, error is going to be talking about how far off are you from a known quantity, an accepted value of some kind in your measurements. Okay, so that's error. So that is different from uncertainty, right, Brendan? Uncertainty can contribute to error. If I have a really big uncertainty, if I did a really crappy job of measuring something and I have a huge uncertainty, then probably I'll have a big error too. But they're not exactly the same thing. I don't have to have a big uncertainty to have a big error. There could be other reasons I have a big error. What do you think, Brendan? Does that answer your question from earlier?
No, that makes sense.
Okay.
That makes perfect sense.
Okay, cool.
Does-
Our last definition we want to talk about is error analysis. People use this term like willy-nilly. And it really means a certain thing. So what is error analysis, do you think?
Like addressing the possible reasons that you had error.
Precisely, yes. And doing that in a quantified way, like using our graphs and seeing how far our points are away from the line, from the curve, to help us figure out what might be wrong with the error. So it's not just like thinking about it, it's like doing some calculations and stuff too. Yes, but yeah, that's what it is. Like determining where the error came from and explaining it to do a better job next time. Okay, questions? All right, I'm going to attempt to put you in breakout rooms, and then I'm going to give you questions to talk about. And then we're going to come back after like 5 minutes and get some answers to the questions. So I think I have to stop screen sharing to do this. Right, and I'm going to do breakout rooms. I'm going to assign manually. Okay. I think I'm going to actually go ahead and put the questions in the chat before I put you in breakout rooms so that you can all see the questions. So that's first. If you don't answer them all, whatever, it's fine. I want you to all at least discuss one question and have one answer when you come back. Oh no, sorry. Chat. Okay, I put some questions into the chat so you can start thinking about those while I put you into breakout rooms. Okay, here we go. Okay, I think you can get into the rooms now. I'm gonna keep assigning them while you go. Okay, I think we got most everybody back. Y'all hear me okay?
Yep.
Okay, so can we have a volunteer from one group take the first question about the speed of light measurement? Anybody want to volunteer, or I can pick someone?
I'll go.
Sean, thank you.
Okay. So the first question I have is it supposed to be to the second power times 10 to the second power?
Yeah.
Okay. So then my group, we said that it was pretty precise, I guess, because it was like to the 10 decimal places. So pretty precise, but obviously they did something really wrong in the calculation because it's not even close to the actual speed of light.
Okay.
So
So is
we
it
just kind of
accurate?
speculated. No,
No.
not at
Okay.
all.
Right.
So I guess we just kind of speculated that either they measured it wrong, or like the measurement devices were bad, or they just did something wrong in calculation, or maybe even possibly they had bad handwriting and they came out that way. 'Cause-
Okay. So when
Well-
I was asking what is contributing most to error, I should have said this maybe a little clearer. Is it precision affecting the error, or is it accuracy affecting the error?
Accuracy.
Right.
Okay.
Okay.
Yeah, that
Thank
makes more
you.
sense.
Thank you, Sean.
Yep.
Okay. Somebody else from another group, please answer the next question using a meter stick, the width of the dime. Caitlin?
Yeah. We said this was neither accurate or precise, both because with talking about like if you stack them straight up, like that's not anywhere close to a centimeter.
Mhm.
And then you shouldn't be using a meter stick because that's way too big of a measurement tool on a dime. You should use something a lot smaller. So that's why like you just didn't use a good tool. It was nowhere close. What else is there? There's a large error. And is that it? Is that enough?
Yeah,
do you want more?
what's contributing most to the error, precision or accuracy? Or both, or neither?
Both.
Yeah,
I'd
I would say both.
Yeah.
Totally. Yes, I agree. Okay. We already covered what is the difference between uncertainty and error earlier. So let's come back to that. One person tell me, what am I doing when I perform error analysis? From another group, please.
I'll go.
Okay.
You're just trying to figure out what could have gone wrong in your measurements.
In your
Like reasons
measurements,
for
just your
why you would have not
measurements?
gotten your desired outcome.
Okay. Is it just measurements or maybe
On your
other things?
procedure measurement.
Sorry, go ahead. I didn't hear you.
It could be anything. Oh, what?
Okay.
I said it could be anything. Anything along the way.
That contributes to that final error. So yeah, you're figuring out what contributed
Yes.
to it, but you're also doing some math, some work, which you haven't learned yet, which we're going to learn about this semester, to get to that point, to perform that error analysis. Totally. Okay, thank you everybody. That was my first time doing breakout rooms, or like putting people in them. So I'm going to do it better next time. There will be more rooms and less people, but I just didn't know I couldn't add rooms after opening them. So next time, better every time. Okay, so I want to talk about some more things, but it looks like we're running out of time. So I do want to show you, I promised to show you the references for this document here that we were looking at earlier. Okay, so all of these rules for error, uncertainty, and all of these things came from several different resources, but mainly from NIST, from like one main actual facility, I should say. Okay, so next time we're going to finish going over our agenda, and we're going to talk about how do I determine the uncertainty of measurement on a voltmeter? How do I determine the uncertainty if the voltmeter is fluctuating or not fluctuating? Do I have the same uncertainty? Is it different? What if I have a pressure gauge? How do I do that? What if I have a meter stick? What if I have a caliper? What if I'm counting like radioactive events with a counter? What's my uncertainty then? If I have an integer value, how do I know how to determine that uncertainty? So that's what we're going to talk about next time, and we'll do some more breakout room examples and then talk about them together. I did record this, so I will be putting this on the As You Learn page just after class. Anybody have questions? Okay, we have 4 minutes, so I'm just going to get started with the first uncertainty thing, and then we'll pick up next time. So I'm going to go back to our PDF document from Introductory Lab. At the very top, we have this nice menu, and we can see there's all these different things listed here. We have an analog device, we have digital readouts, and then more complex things like standard error of the mean. Standard error of the mean is a concept we're going to talk about more in detail in later weeks, so we're not going to go too deep into that this time, but we are going to go through these main basically analog and digital meter device kind of things. All right, paging down to the analog example. Okay, now I know you've all used a meter stick before to measure the length of something. In this fabulous example, we have a meter stick and a pin. And we are going to determine the length of the pin with the uncertainty in this example. A little bit above, it tells us the rules for determining the uncertainty up here. I'm not going to go through those. I'm going to go through the example. It goes through the rules just with the example. But if you feel like you want to look at those rules, there they are on the previous page. All right, so there's our pin, there's our meter stick. We can zoom in on the left-hand side of the pin and the right-hand side of the pin to help us determine exactly where the pin is lining up on the meter stick to determine its length. So this is what we do. We follow these steps. we determine the smallest increment on our measuring tool. In this case, we have a centimeter from 29 to 30, and that's divided into 10 bits. So we have 0.1 centimeters is our smallest like division unit width. Our smallest increment is 0.1 centimeters here. Okay, and that's number 1. Now I'm going to see from the tick marks, I can read 21.4 centimeters, definitely from the tick marks, as far as the distance between those two things. But maybe I can get it to another digit. Estimate one more digit. Okay, now I need to make a decision. I need to decide if I can split that increment into segments. And I have to make that decision based on like how well I can literally see that meter stick. It might be in really bad shape and I might be able to not be able to see anything, or my glasses might be smudged. I'm going to make a decision either way. All right, we've reached 4:50, so I'm going to have to stop now. I'm so sorry. We will finish with this very exciting example next week, the measurement of a pen. Try not to get too hung up on it. And if you have questions, I'm happy to answer them. Otherwise, see you later. Have a good weekend.
Thank you.
Thank you.
Have a great weekend.
You too. Okay, and I'm stopping recording.